Introduction to Systems, Part 1. We're going to learn on the concept of system and the system classification. So, a system is a mathematical transformation of an input signal or signals into an output signal or signals. So, we have an input signal over here coming into a system, then it will produce the output signal. So a signal is a set of data or information, or a function or sequence of values that represents the information. And it is also a function of one or more variables, such as time, frequency, and space that conveys the information. Whereas a system is an entity that processes a set of signal, which is the incoming input signal, to yield another set of signals, which would be the output signal. So here, the first diagram is showing you the excitation signal, which is the incoming signal, the input signal, xt. It will enter into a system, which is denoted by this block over here, and it will give you the output signal, which is the response. So usually we will denote the excitation or the incoming signal as xt, and the output signal is denoted by yt. Hence the equation over here, yt is equal to h is the system, times with the incoming signal, which is xt. So here you will have the information signal coming through the system. So here the system consists of three parts: the transmitter, the channel, and also the receiver. So it will enter transmitter, transmission channel, and finally the receiver. At the end, it will produce you the information signal in terms of output signal. So why does you have noisy information signal over here? It's because when the incoming signal goes through the system, there will be noises coming over into each of the block. So you have noise coming into the transmitter, noise occurring inside the transmission channel, noise occurring in the receiver. So that's why you will have an information signal that have noises, which is not ideal. An electrical circuit viewed as a system. So this diagram is showing you an RC low pass filter. It is excited by a voltage V in, so that would be the input, and responds with the voltage, which is V out. This would be the output. It can be viewed or modeled as a single input, single output system. So you have the incoming signal V in going into the system, which is denoted by H, and finally produce you an output, which is denoted by V out. Just like signals, you can also classify your systems. So you can classify it in terms of linear versus nonlinear, time invariant versus time varying, memoryless versus with memory, causal versus non-causal, continuous versus discrete, analog versus digital, invertible versus non-invertible, and stable versus unstable. Linearity. So a system is said to be linear in terms of the system input, which is xt, and the system output, which is yt, if it satisfies the following two properties of First is superposition, and the second one is homogeneity. So superposition means that when you have xt is equal to x1t, so you will have an output of y1t. If you have another signal coming through the system, x2t, this will produce you an output which is y2t. So combining this together, you will have xt is equal to x1 plus x2. So the total output yt would be y1t plus y2t. Homogeneity or scaling is that when you have xt produce yt, so any scaling that happens at xt will also be scaled at the output as well. So when you have a constant factor axt, this will produce an output of ayt. Next, we have time invariance. So a system is said to be time invariant if a time delay or time advance of the input signal leads to an identical time shift in the output signal. So here, the first diagram is showing you a signal coming into a delay system. So delay system is st0, and then this will produce an output of x1 t minus t0 because it has been delayed. And then it comes over into the another system operator which is denoted by h, and this will give you the final output which is y2t. The second diagram is showing you an incoming signal that goes into the system operator h first. So this will produce an output of y1t. After that, it will enter into the time delay system, which is denoted by st0, and this will give you an output of y1 t minus t0. So these two situations are actually equivalent, provided that h is time invariant. Time invariant system is one whose parameters do not change with the time. So a system is time invariant if when the input is shifted in time, then its output is shifted by the same amount. If you refer to this diagram over here, when you have xt, this one starts at 0, you produce an output that also starts at 0. The second diagram is showing you xt minus big T, which is the period. So it actually starts at this point. So the output will also be shifted by the same amount. It will also start at the big T. Next, we have instantaneous and dynamic system, or memoryless versus memory. In general, a system output at time t would depend on the entire past input. So this system is called a dynamic system, or a system with memory. But when you have a system that the past history is irrelevant in determining the response, this would be an instantaneous system, or a system that is memoryless, no memory. So again, a system that has memory if the response depends on the past or future excitation. It depends on the. It is also called as dynamic system. But if you have a system that has no memory, if the response depends only on the present excitation, so this is called as static system or instantaneous. Now we have two equations over here. Can you have a guess which one is memory and which one is memoryless? Yes, the first one is a memory system, while the second one is a memoryless system. Why is that? Because the first equation over here is depending on the past excitation when you have t minus 1 and t minus 2. The second equation is not depending on any past or future excitation. So that's why it is memoryless. Next one, an example of a memoryless system. The output of a memoryless system at some time t0 depends only on its input at the same time. So here you have a resistive divider network. A resistive divider network only depends on the input at the same time. So you're not actually depending on any past or future excitation. And here you have an example of a memory or dynamic system. Note that the Vt depends not just on It at the present time, but it also depends on the past of It for the infinite past. Therefore, this system is a memory system. Now, is a resistor that applies Ohm's law memory or memoryless system? Justify this. A resistor is a memoryless because the current IT responds to the applied voltage at the present time only. So when you have an equation over here, it clearly shows that this one is a memoryless system. Next, if you have an inductor across an applied voltage, is it a memory or a memoryless system? This one is a memory system because it depends on all the past values of the voltage as shown in the equation.